Next slide, please. Thank you. So introducing our panelists, we have Ernie Noviello, who's our subject matter expert on all things check valve and NIT related. Ernie has over 30 years of experience in diagnostics, and he's been involved with numerous customers on improving their check valve programs. He's also a member and chairman of the ASME O&M 22 subgroup committee with extensive involvement with the NIC group. You'll also hear from Stan Hale, who has over 35 years of experience in the nuclear industry and has provided testing, engineering, and analysis support for most power plants in the US and overseas. Stan is also a member of the ASME O&M working group on MOVs and a member of the ISA working group on automated valves. And we have Griselda Alvarez, who's our marketing manager, who has championed our efforts on setting up the webinar. She will be collating questions from the Q&A section and fielding them to our panelist group at the end of the presentation. So going over our agenda for today, we will discuss why non-intrusive testing should be considered a major part of your condition monitoring program, and we'll lay the case for it. We'll also look at the regulatory history, which leads us to present-day environment, review the basket of non-intrusive testing technologies developed by Crane and the associated benefits. We'll also share our most recent operating experience, or OE, as a case study with the Surry Nuclear Power Station. And finally, we'll wrap up with question and answers. So as all of us are acutely aware, we as an industry are challenged by market conditions to cost-effectively compete while maintaining safety as a number one objective. The call for action here is to look for innovative solutions that is technology-driven and brings about process change to significantly reduce costs while allowing resources and personnel to be deployed in more productive areas to drive true productivity. Distilling this objective down to what it means for check valves brings us to the discussion of Disassembly and Inspection, or D&I, where experience has shown that it can be time-consuming, resource-intensive, with the potential to introduce human errors. Now, D&I has been widely adopted by the industry over the course of time to establish operability. As a result, D&I is performed today as part of condition monitoring efforts where acceptable and proven alternatives exist in non-intrusive testing. Next slide. As Ernie will expand from here, D&I has a place for you in the check valve program, but our message in this webinar is to lead with non-intrusive testing for valves that do not require D&I. The Appendix 2 also allows the use of NIT as part of your condition monitoring program with the supporting trendable data that permits test interval frequency extensions for up to 16 years. We have slides later on that substantiate some of this. So at this moment, we will pause here for a few seconds to get a quick poll to help us understand if your IST program is set up to take advantage of Appendix 2 NIT. In other words, does your program document refers to NIT as a method to support testing? So this pop-up will appear on your screen, and if you could take a few seconds to answer that, that'd be fantastic. I'm going to hand it over to Ernie now to walk us through the industry regulatory history. Ernie, you can take it over.
Okay, so let's go to the next slide. Appreciate everybody joining us today. I trust that you'll get a fair amount of information. We've spent a pretty good amount of time putting this together, and I believe everybody will benefit pretty well from it. So this particular slide right here, this shows us not 100%, but pretty close to all the major efforts that have taken place with the development and application of non-intrusive testing. I'm not going to go through every single one. The slide is there, you'll have access to it, but really the takeaway here is check valve non-intrusive testing has been thoroughly vetted by rigorous industry-sponsored research. There's a lot of time, effort, and cost of utilities that have gone in to the development and application of non-intrusive testing. So that's one of the major points that I wanted to get across. It's not cutting it. It's not something that's being trialed and tested. It's been developed. It's been tested. It's been vetted, and now a lot of utilities are really taking advantage of the benefits of non-intrusive. Did I get the next slide? So the main driver, of course, of what we do in diagnostic check valve testing comes out of the ASME OM code. And just a couple of tidbits out of the code, ISTC 5220, 5221. ISTC states that in subparagraph A, the necessary valve obturator, which of course is the piston, disc, whatever is inside the check valve, its movement during exercise testing shall be demonstrated by performing an open and closed test. And most of us understand that to be bidirectional testing. B is something that you may have a small population of, maybe some cases a moderate population of, but it's not the most common aspect of a check valve design is the mechanical exerciser. And in this case, you have to assign acceptance criteria to that. C tells us that if the test methods in A and B are impractical for certain check valves, then, or if sufficient flow cannot be achieved or verified, then a sample D&I program is used to verify valve obturator movement. So that kind of speaks into disassembly if you can't achieve A and B above. But the next slide will tell us a little bit more about where we're going. So ISTC 5222 talks about the condition monitoring program. Now, I trust that majority of plants are into Appendix 2, into condition monitoring, although I know there are probably some that are still in ISTC space. But for the purpose of this discussion, we're going to spend a fair amount of time on Appendix 2 just because of the significant benefits allowed by using Appendix 2. The ISTC 5222 says as an alternative to testing or exam requirements of ISTC 3510, 3520, 3530, 3550, and 5221, the owner may establish a condition monitoring program. So the purpose is to improve valve performance and optimize testing, examination, preventative maintenance activities in order to maintain continued acceptable performance of a select group of check valves. The owner may implement this program on a valve or group of valves, shall be implemented in accordance with Division 1 Mandatory Appendix 2 Check Valve Condition Monitoring Program. So it becomes mandatory when you elect to use Appendix 2. And in this particular situation, just the best way to summarize this is a optimized program where ISTC is more a prescriptive program. In code space, there's a lot of time and effort to establish the Appendix 2 program for the purpose of using a lot of history that we already have to benefit the efficiency of our check valve program. Okay, this is something that was just released the end of 2019. I served as a technical advisory group member on this particular committee. And I think the main takeaway here is in this EPRI guidance 4.4.2.2, it talks about the ASME OM 22 working group. And ISTC was developed by ASME on check valves OM 22 performance testing. And it talks about the recent code version confirms the acceptability of non-intrusive monitoring techniques for confirming valve disc movement and position, and endorses and provides guidance for the use of a sampling rather than 100% basis for inspection of valves disassembled in lieu of check valve exercising as suggested by NRC in the generic letter 8904. So again, this is discussion about a optimized program. And the last sentence there says the direction of these documents is to place increased reliance on testing and surveillance monitoring and decreased reliance on frequent disassembly and physical inspection. The reason for this is the history has proven that a disassembly and inspection for no good reason is likely going to produce situations that are going to be more detrimental. In other words, the best way for me to say it is that it's not the best practice to take apart a perfectly good check valve just to verify the operator can move back and forth. There are other ways to do it. And again, in this particular slide, it speaks to the acceptability of non-intrusive monitoring techniques. Now, I know I've heard a lot of people who are somewhat confused about using non-intrusive and where you can use it and how you can use it and baselines and everything else. But the bottom line is it's an acceptable means equal to disassembly inspection to implement your program. So again, the real takeaway here, and this is a reiteration of a message that you heard Ron speak into, it's the recommended best practice would be to lead with NIT and selectively use DNI. Every time I present to the industry, I always say, this is not your answer for everything, because it's not. And using it where it's most appropriate is where you're going to get the biggest benefit. But if you have a situation where the valve has to come apart for modification, maintenance, whatever the case is, then it has to come apart. But if you're just taking it apart, especially with backup safety systems that see no service, then there's a good chance you're going to incur much more potential problematic issue than not with a disassembly inspection. One thing's for sure, it's going to cost you more and it's going to take more time. Okay, so another poll question. How many check valves do you believe may eventually be candidates for Appendix 2 NIT? Your best guess, I know if you're IST engineers or check valve engineers, you probably have access to the information. If you're not, no worries. But you may, if you're in maintenance or CMO, you may be aware of certain big hitters of valves that are coming apart every outage. And people ask the question, why are we taking this valve apart? So there may be a population in your mind between 1 and 10 or whatever the case is. So just answer it the best of your ability. I believe we're going to send out the poll responses to everybody too, or discuss that so everybody can kind of see what the majority of thought processes are. All right, so I'm just going to give a high-level overview of the NIT non-intrusive testing technologies that we have, and these were developed 30 years ago, and we've been applying them regularly and providing, I would say, extremely beneficial results for our customers. We have 3 technologies we rely on. One is acoustics. Acoustics we match with either one of the other look technologies. Acoustics is our hear technology. And one of the things we've done with the acoustics is we put in a power spectral density algorithm that is able to automatically determine impact rate, magnitude, and frequency events. And then we can use that to trend over time to look for changes. In terms of technology processes, this provides us the highest statistical accuracy of making sense out of the data. The other aspect, of course, the PSD comes from the time domain data, but you have the ability to see the time domain data. You can look at the waveforms because they do tell certain things about metal impacts. You can look at techniques such as time of arrival to determine, did it hit the backstop? You can listen to audible indication. But the industry has looked at a couple specific cases, and one is the IED 2021. It's a Palisades incident where certain technical findings that had come out of that. And the bottom line of acoustics is you want to avoid using it all by itself. It can trick you because of certain aspects of plane interference and other types of noise. So coupling it with one of the look technologies, in this case, our first and probably one that we rely heavily on is ultrasonics. It's a look approach. It sends high frequency sound wave down into the part. And we're able to determine the disc open angle in degrees off the seat and the disc angular velocity. Those are very important attributes, and they're actually trendable attributes. They're attributes that we have used to trend certain valve condition and provide disassembly inspection recommendations at plants throughout the industry. The other aspect of using that is for stroke test. And in the case of a stroke test, we can use the technology to mark where the operator starts to transition from close to open or open to close. And then the third technology, or the second look technology, uses eddy Kerner's pulsed electromagnetic. The look approach, using surface eddy currents, the disc travels through the electrical field, the eddy currents displace, and then the software provides us a change in voltage. It's something providing us disc movement position. We can overlay traces, and we can make determinations of what's changed from test to test. All right, before we start this graphic, I just want to give you an idea of what you're going to see. The valve's going to open up, and you're going to see the ultrasonic transducer emitting little ultrasonic waves. It's going to go up, it's going to hit the disc in a closed position. The right hand of this side of the screen shows really the A-scan representation of what happens to the reflector in terms of magnitude over time or over distance. And then when it comes in the open position, it's going to show a change in sound path, and that would be the point where we would obtain what we call steady state data. The steady state data is to give us an indication of, will that disc flutter allow the accelerated wear probability to occur? And then when the disc closes on cessation of flow, we'll actually watch that signal come back and be able to determine where the closed position is and if it lines up with the initial closed position, if the valve has closed all the way. And the bottom of that trace is just what the software shows. This is actually a modeling of it was a turbine-driven discharge check valve at Indian Point. It's a 4-inch or 6-inch crane model. And this is actually how slow the valve closes with a turbine-driven system, aux seawater. This shows what the eddy current probes, they'd be placed on the seat and at the backstop, those little bubble-like graphics. As the disc moves from closed to open, the eddy current again shows a change in voltage. And when it goes from closed to open, and we have confirmed the full stroke, we can assign what we call a stroke delta to the valve, and we can overlay that in the future to see if it's traveling the same distance or if maybe it's hung up or stuck or whatever the case is. We've actually used it in numerous occasions to show us valves that were stuck. Okay, so just summarize the benefits of using non-intrusive. In terms of Appendix 2, you can actually get to 16-year interval extensions with a group of 3 or 4 valves. That's just based on the rules of Appendix 2. But if you're testing a valve every outage or just disassembling and inspecting one every outage, then you can see where Appendix 2 is going to provide a huge benefit in terms of, using reliability data to say the valve's going to be okay. This significantly reduces the cost of DNI. I'll show you here in a slide or two coming that we did a cost study. Just basically, it's about 1/8 of the cost. These are conservative numbers to say 1/8 of the cost to disassemble non-intrusively test versus disassembly and inspect. I know in some cases it far exceeds 1/8 of the cost. We're providing industry-proven trendable attributes. There's a lot of discussion in the industry about what are industry-proven or acceptable trendable attributes. So one thing we've done with our technology over the course of years of development have assigned trendable attributes. And those trendable attributes exist to show us changes from certain conditions, and then we can reliably predict. We use those trendable attributes during the NIC phase 4 testing. So there's a lot of science behind that. We're going to reduce or eliminate planning time. You can imagine how that works. Eliminate the support for clearances. In other words, clearances are a big issue, and you need no clearances to perform non-intrusive testing. FME is a big issue. You don't take the check valve apart, you 100% eliminate the possibility of foreign material. We're going to greatly reduce personnel injury risk. There are numerous OE where check valve disassembly inspections have constituted personal injury, and in our business, we know personal injury is just not a good thing. Tagging violations, you're going to eliminate those. You're going to eliminate maintenance-induced failures, and regardless of what we may think we know, that's a pretty substantial aspect of disassembly inspection. Things go wrong. Check valves can go back in incorrectly, they can be broken, parts might not be available, whatever. It can be a problem. And then we're going to reduce or eliminate, rad waste as a result of, not taking check valves apart and all the aspects that go along with that. So here's the cost breakdown. I'm not going to go through it line by line, but we worked up, as I said, 1/8 of the cost, non-intrusive to do the DNI. And you can see the certain things that don't exist in the right column do exist in the left column, like the clearance, preparations, parts cost, potential cost of maintenance-induced errors. Scaffold setup and tear down is something that still is probably likely to happen with non-intrusive. However, there are certain situations out there. We've developed certain accessories that, extension rods and whatever, we can actually reach valves up to 8 feet away. That would remove the requirement for scaffold on a check valve. So here we are with another poll. What do you estimate the annual financial impact of adopting check valve non-intrusive testing could be at your facility? Again, if you're involved in the check valve program, you probably know, but based upon the table we gave, if you have an idea that there may be 2, 3, 4 check valves, whatever the case, you could use that $28,000 figure that we've come up with. But if you can just take the minute to answer that poll. Okay, I'm going to discuss and conclude my part of this presentation with a Surry Power Station non-intrusive test case study. In other words, crane nuclear support of Surry's condition monitoring program. And this just occurred this outage season, March, April timeframe. Okay, so the condition monitoring program review, I was contacted by the site to do a review on the newest condition monitoring program. The objective in this case was to enhance specific areas of the existing check valve IST program, or I should say the updated IST program, which is in preparation to facilitate Appendix 2 non-intrusive testing adoption. Was involved in reviewing and still reviewing some of the newly revised condition monitoring program documents, essentially for Appendix 2 3000 purposes, and the applicability, including failures, trends, industry OE, in certain specialized areas. Provided recommendations and continuing to provide recommendations for industry OE and non-intrusive test applicability, and then revision to condition monitoring plans that will address non-intrusive for certain recommended populations. All right, there was a scope of 20 check valves total that we were involved in testing at Surry. And one population, we actually were testing the check valves to verify valve operator stability. The non-intrusive testing was performed to supplement flow testing and leak testing. That was already a part of the condition monitoring plans on populations of valves that had infrequent maintenance activities, such as disassembly inspection. We used ultrasonics to show operator stability or instability on valves that were in service constantly, like boric acid component cooling water. When the valve's in service constantly, that's the likely candidate for a valve that's going to experience accelerated wear. The valves are being, back up please. The valves are being flow tested and back leak tested with no disassembly inspection to augment as defined in the condition monitoring plan. And we used ultrasonics to provide what we have a crane nuclear disk stability classification or data regarding the propensity to experience accelerated wear. In this case, for these particular systems, every valve that we tested indicated stable condition with no expected accelerated wear. In other words, these valves were stable, and if the check valve is stable and full open, held against the backstop, then it's not going to experience accelerated wear. A second population was tested to determine a closed position. So this is something we do a significant amount of work through the industry. Again, when condition monitoring came into play, you have populations of valves that may have, not had any other than the safety position verification, of course. But now bidirectional testing requires testing in both directions. So that could create a challenge, and it did create a challenge in a lot of cases. In most situations, the flow test is relatively available and fairly easy to accomplish. So the flow test generally determines the valve's open. But the non-safety position in most populations could be the closed position, and that's where the problem and the challenges come in. So the disassembly inspection, or trying to figure out, in other words, making a category A type of requirement for a category C check valve to leak test it, could usually create problems. So we can come in with ultrasonics and use either pulse echo, which is single beam, or through transmission, which is a two transducer technique, pitch and catch, to position the ultrasonic beam in a location where we know that the disc would be if it were off the seat. So we can fast and effective means to determine the obturator position. Again, it's not intended for Category A check valves. Category A check valves are required to be leak tested. The big takeaway here was they have a main feed water discharge check valve inside containment. We're able to non-intrusively test it with pitch catch and with pulse echo in 15 minutes as compared to a complete 3 days of disassembly inspection or 288 man-hours saved. Just to give a little bit more information, this particular valve, it was a Surry thing, but this particular valve had the bonnet welded together, and they had to actually cut the bonnet, that weld, out to access the valve, and then they had to re-weld that bonnet back in place. Okay, so we also tested the auxiliary feed water motor-driven and turbine-driven discharge check valves, used ultrasonics to determine the disc stability and the position of the disc. These two attributes align with good information. In other words, if the disc is stable, usually it's going to be held in the full open position, and the ultrasonics can tell us the angular position of the disc as well as the stability. The motor-driven valves, two in each unit, in this case, unit 1, the motor-driven valves were determined to be stable and full open after they transitioned from minimum flow. Of course, in this test, I think most aux feed tests start on minimum flow and then they run the flow up. Another thing Surry had done this particular outage was they had disassembled both of these valves, and then the disassembly inspection results aligned with the non-intrusive data. The non-intrusive data suggested that the valves were full open and stable. There would be no propensity for accelerated wear, and that's what they found during the disassemblies. The Unit 1 turbine-driven discharge check valve was determined to have very high excessive angular velocity, in other words, a lot of disc flutter. And best we can determine, it suggests a similar condition that contributed to the Unit 2 valve failure. When we go to Surry in the fall of this year, we'll be testing that Unit 2 check valve to confirm the assessment. But it's pretty likely that what we saw in Unit 1 is probably going to show itself in Unit 2, and that excessive movement in that valve is likely the cause of the failure. Okay, so we established the non-intrusive test baseline. We provided trendable attributes that again align with our involvement and the qualification, if you will, of the trendable attributes during the NIC Phase 4 test program. As we establish another data point, and the future trends will be evaluated to go ahead and adjust the test frequencies allowed by Appendix 2. And the same scope that we just did 20 valves for Unit 2, Unit 1 will be doing the same thing for Unit 2 in the fall of this year. Program questions can be addressed with Mr. John Reno, john.reno@dominionenergy.com. So I know he's available to answer any specific Surry program questions. And I do want to thank those individuals from Surry, for supporting that aspect of our presentation. So here's a graphic, and I don't want to leave this day without just touching on the fact that we've conducted supplemental position indication testing at a couple plants, and we're actively involved and engaged in providing solutions for that. This particular graphic, when we run it, is going to show how we're able to determine with the same ultrasonic techniques that have been qualified for check valves to be able to apply those for power operated valves. Here's a globe valve, one of the more common AOVs. And in this case, as we run the graphic, you can see the ultrasonic sound path bottom right change as the operator position changes. And that will repeat itself. If the operator and the stem become detached, then basically the graphics show us that the operator position has not changed. It's a relatively fast and easy technique. And again, I know supplemental position indication is creating a lot of challenges throughout the industry. We're positioned pretty well for this technology. And although we're showing a globe valve here, we've got ability to test gate valves, butterfly valves, other types of styles of valves. So at this point, I'm going to turn it over to Stan Hale.
Dan, you've got to come off mute.
Great idea, because I was really talking right there. Thanks, Ernie. Before we close out today, I just want to circle back to Ernie's timeline for a few minutes before we close. We started working on check valve NIT, and that includes the acoustic and ultrasonic technologies that Ernie discussed when SOER 8603 was being written and about ready for issue. And that's right. I'm that old, and this technology is also that old. I first tested check valves with what we called Checkmate at that time in 1988 at Utah State as part of a utility-sponsored initiative that was led by San Onofre. They had some fairly significant check valve issues back at that time, and I believe they're referenced in 8603. There were a number of plants that participated, and our objective at that time was to identify promising technologies for check valve testing. My real point in all this is this stuff's been around for a while, 30 years in fact, and it's been thoroughly vetted. Ernie referred to that earlier in the presentation. The application and the limitations are well understood. We're not in R&D with this stuff. Oak Ridge evaluated check valve monitoring in the late 80s, including the acoustics and ultrasonics that we've been talking about here. The nuclear industry check valve group went through a seemingly endless number of testing projects aimed at verification of the technology. The ASME check valve working group gave us Appendix 2 back in 1996. The NRC approved that when they adopted that version of the OM code in 99 without comment or exception. EPRI's looked at this. Ernie referred to their report that came out in 2019. 51% of the nuclear plants in the US own and use some degree of our check valve technology. There are several plants that own a competitor's acoustic system, but what surprises me most is in 2021, there's still about 20% of the US industry that does not do any level of check valve NIT. That's a fair number of plants. If you're not taking advantage of the benefits this technology provides, you're missing an opportunity. Now, as discussed, NIT is not a panacea. You have to think about what you're doing and how to use the data. That's where the trendable attributes come into play. If the data shows the valve is not rattling the acoustic sensors and the valve moves effortlessly from one position to the other, do you really need to take it apart to see the same things? You know, now, it doesn't mean you won't ever have to take it apart again because things will degrade and things will change, but that will be a far less frequent and far less costly paradigm, right? Our thinking, and all the way back into the 80s, was if one, the acoustic attributes from steady flow when the valve is new do not change over time, then the tolerances within the valve should be essentially the same, right? We shouldn't have, you know, a gap between our hinge pin and disc that allows the actuator, as Ernie calls it, to rattle around. If the disc moves effortlessly from the closed position to the open position and then falls back when flow is removed, as you see in the UT, then you have a stable, well-designed disc, and it should last for an extended period of time. However, if we see the acoustics start to indicate a lot of rattling, that the disc is bouncing around on the hinge pin or moving around like it should not be, then something's wearing there. And if we see a valve disc that is sitting fluttering in the flow stream, we used to call that walking, because what we do is look at that number and we calculate a disc stability number, but what it's really telling us is how much those surface areas are going to move across each other over an extended period of time. And if you put a disc on a pin and you allow it to wobble in the flow stream for 5 or 6 years, eventually it's going to completely disappear. It's going to wear out and cause a problem. So what we're trying to do with these webinars is just share this OE, share this experience on the technology, and hopefully help you guys improve your programs and become more competitive as an industry. So Ernie, next slide. I think we have one more here. So this is our first webinar. We plan to have another, and there may be others. So we invite you to join us again on July the 8th, where we're going to go into even more detail. We hope to just keep sharing this and hopefully bring everybody up to speed and help you understand how this technology works and how to apply it. And I think now we're going to review some of the questions that were submitted, right, Griselda? Do we have questions that you're going to pose for Ernie or others at this point?
Yeah, so we actually had a couple of questions come in for you, Ernie. So one of them was, Ernie, can you give a general idea of how many sites are currently self-sufficient in performing NIT on their IST valves, meaning proficient individuals in CMO and or ISO groups performing the tests?
I don't really think I could answer that question, because I think the sites, of course, that we don't have work or we don't own our platforms, I wouldn't really have any idea. The sites that we have access to, I probably would consider 70% of those sites or 80% of those sites may continue to rely on services from us or some level of support from us. I think the main reason for that is that acquiring the skills to perform non-intrusive testing and then collecting the data and then analyzing the data, it's something that requires applied time, and in most cases an 18-month refueling outage cycle, or best case maybe every 6 months. It may be easier to maintain that proficiency, but that's a personal choice, and I find that that's mainly an aptitude thing. If the person at that site, and I've seen people who just have really, they're able to gather the skills quickly and apply them quickly, so then it just becomes whatever the person feels comfortable with. So I hope that answers your question best I can.
Okay, and then we had another one come in. I believe this one came in when you were talking about the case study, and the question was, did you say that we cannot in situ leak-rated check valves?
Could you please repeat that question?
The question was, did you say that we cannot in situ leak-rated check valves?
I still didn't get the word after we could not something, a check valve?
Yes.
I'm not understanding that question. I'm not really understanding some of the words. In situ? Was that in situ?
Yes.
Okay. So please repeat it again so I can try to really understand. We cannot in situ a check valve?
Leak-rated valve.
Yeah, so I'm not sure what that question is referring to. Here's what I can say, hopefully to answer your question. We don't use non-intrusive on category A check valves. In other words, they are designed and they have specified seat leak criteria. Regulation requires that. So we don't generally do much pending category A check valves with non-intrusive. It's not the best, it's not the right application. You already have a non-intrusive technology in terms of a, well, maybe somewhat non-intrusive, but you're already using Appendix J for the purpose of verifying the valves closed, likely flow to verify the valves open, and those are generally your condition monitoring test methods. So non-intrusive would not provide any benefit or application for category A. So I guess I didn't say, I was misunderstood. You can certainly in situ a category A check valve, but not with non-intrusive testing.
There was a little bit of clarification that came in, Ernie, and they say, Ernie, the question was on eliminating the need to LLRT with NIT.
Oh yeah, no way. That's not in the same wheelhouse. So we're not proposing that you could ever replace the Appendix J test with non-intrusive testing. You could potentially use it if you're interested in seeing the condition. If there's a situation where you wanted to see, was the valve experiencing accelerated wear, then you could use it in certain applications to, provide some additional detail about the valve, but never could non-intrusive testing replace the Appendix J testing. Two different
Hey, I think
animals.
I can help you a little bit here, Ernie. Acoustic emission leak detection is different from the acoustic vibration testing that we're doing with check valves. The acoustic vibration testing we're doing is much lower frequency. It's down, 25 kilohertz or less. It's in mostly the audible range. If you're using acoustic emission for leak testing, like has been used in some of the Appendix J test programs, that's a different type of transducer. It's a much higher frequency that's going to operate up over 100 kilohertz, really, really high frequency. And it is very good for detecting leakage through valves, but it's not a quantifiable thing. It can give you small, medium, or large, but not exact liters per minute or cc's per second or whatever we're looking for. That's not possible. So you could augment check valve NIT with high frequency acoustics for leakage, but that's not really the purpose. What we're looking for is change in behavior within the valve. Our tolerance is increasing that are allowing rattling, more or less, that allows the valve to move around, and that's different. So hopefully that helped a little bit, or confuse things even more.
Again, just to reiterate a little more on that subject, then we're really using it for bidirectional non-safety position for the most part, although it could be bidirectional safety position, as well as most of the BLP systems for determination of propensity to wear. So in other words, instead of taking a valve apart to see if it's worn, you can use the diagnostics to say that there's a condition that's going to lead to accelerated wear, and then we'll help you pick the most optimum disassembly cycle, or be able to say the valve's stable and it's not going to experience accelerated wear.
Okay, at this point, if there are any additional questions, you can use the raise my hand feature that should be on the right-hand side of your screen. I can unmute you and you can ask your question. You can also submit it via the Q&A feature as well if you'd like. Okay, looks like we don't have any additional questions for you, Ernie. I think that'll wrap up for today, our webinar. So thanks everyone for joining. We will, like Stan said, we will have a second one coming up on July 8th, so keep an eye out for that.
Thanks everyone for attending.
Thank you, everybody.
Thanks,
Thank you.